All right, so again, welcome. We'll be looking at worksheet 6 problems. And the first problem that we'll look at is um, one here, which is asking us to find the limits as x tends to 0 from the positive side of x to the sine x using L'Hopital's rule. Now, as we substitute in the value of x, which is 0, we find that we have the indeterminate form 0 to the 0, right? And we can recall from our exponential functions that when you have e to the ln of a function f of x, that is equal to f of x. So in our case, f of x is equal to x to the sine x. So when you substitute x to the sine x into this identity, what you get is that e to the ln of x to the sine x, therefore, must be equal to x to the sine x, right? So they're basically the same thing. Now, how is that important for us? Well, it means, for our case, that when you're trying to find the limits as x tends to 0 from the positive side of x to the sine x, you might as well use the limits, right? Sorry, just let me copy and paste that there. So when you're trying to find the limits as x tends to positive to 0 from a positive side of x to the sine x, you might as well find the limit as x tends to 0 from the positive side of e to the ln x to the sine x, because they are the same thing, right? That's actually a very important development, because then it helps you to sort of manipulate this expression. Of course, you remember from your logarithmic functions that when you have ln of x to some exponent, that exponent can come out, right? So you can have then, right, if you try to rewrite this expression, you can have that's the exponents there, which is sine x, can come out of the logarithmic expression and stay here, right? So now you have limits as x tends to 0 from the positive side of e to the sine x times x, right? So now, at this point, if you substitute x, you will see that you still get e to the sine of 0 is 0. So e to the 0 times ln of 0, which tends to ln of x as x tends to 0, which is not the same as ln of 0, so be careful there. Ln of x as it tends to 0 is, from the positive side, is equal to infinity, right? It's negative infinity to be precise. But so you have 0 times infinity, which is an indeterminate form. So you have to keep on going with your manipulation, because that doesn't allow you to apply L'Hopital's rule. So now, when you note, what you notice here is that you can rewrite this expression as well as, so the sine x here, you can put it in some sort of denominator, right? To have that. So the limit as x tends to 0 from the positive side of e to the ln x divided by 1 over sine x. Now, what happens when you substitute the value of x here? You have ln as ln of x as x tends to 0 from the positive side is infinity, like we said. So you have e basically to the infinity. Just copy the infinity sign. I should have it nearby. There you go. So it's e to the infinity, right? Divided by what? Divided by 1 over sine of 0, and which is 1 over 0, which is close to infinity, right? Because remember, you're dividing 1 over sine of x as x tends to 0 from the positive side. So x tends to 0, but is not equal to 0, right? So there's a difference there. So you have 1 over a very small value that is tending to 0, that gives you infinity, right? So it gives you infinity as well there. So then you have e to the infinity over infinity, which is interesting because then you have infinity over infinity, which is one of the forms where you can apply L'Hopital's rule, right? So now you can apply L'Hopital's rule on this form of the equation, right? So let's rewrite that. Again, you also remember the identity that you when you have the limits on the outside of an exponent of a function, you can just bring the limits inside the exponent, right? So this is basically equal to e to the limits, e to the limits e to the limits of ln x divided by 1 over sine x. And you can evaluate this limits in there by applying L'Hopital's rule. And L'Hopital's rule says you have to derive the numerator separately and the denominator separately. So what happens when you derive the numerator? What's the derivative of ln of x? That's my question to you guys. What's the derivative of ln of x?
1 over x.
Right, so you have 1 over x in the numerator. What's the derivative of 1 over sine x? You guys should also be able to do this. What's the derivative of 1 over sine x?
It is 1 over root of 1 minus x squared.
No, it's not.
Is it not the inverse?
No, that's the derivative of the inverse.
Oh.
There's the inverse function sine. Okay, so please let me just write it down here as well. So okay, so let me just sort of write it.
1 over cosec.
It's cos x 1 minus cos sine squared.
Sorry?
It's cos x and 1 all over 1 minus sine squared.
All over 1 minus sine squared. Okay, no. I feel like you guys are complicating yourself here. So let's note. Wait. Let's note a few things. So first, you can recall that 1 over sine x. 1 over sine x is equal to what? 1 over sine x is the same as just cosec of x. Right. So if you want, you can just substitute that into that, okay? So let's substitute cosec of x there. It's just so we have a simpler form. Maybe makes more sense. Just give me a minute. Please mute yourself if you're not asking a question. right? And then also remember, if I could copy it there, remember that 1 over sine of x is not the same as sine inverse of x. Those are two different things, okay? Right, so please just note this, okay? So what's the derivative of cosec of x? Remember that you guys need to sort of be aware of these rules, these small derivatives quickly, because when you're in a big test or in an exam, you need to work fast. You're working based on time, so you need to work very fast. And so um it might be uh in your best interest to sort of know by heart these sort of derivatives. So what's the derivative of cosec of x, or 1 over sine, which is the same as 1 over sine?
It's negative cosec x times cot x.
Yes, right. So it's negative. Does everyone understand where we got that first? Let me ask that.
No.
Okay, then I'll go through where that comes from, so it can be sort of a practice for our differentiation problems. Yes.
Jonathan, are you sharing screen? Are you sharing screen?
Sorry?
Are you sharing screen?
Yes, I'm showing the screen, yes.
I mean, on my laptop, your screen is not visible. I don't know whether it's me only or it's okay
It's
to
not.
everyone.
I don't know what's going on. I don't know really, because it's showing up here and it's showing that I'm sharing. So let me see. Yeah, it's showing that I'm
Can
sharing.
everyone verify if they can see your screen?
Yeah, I checked already. You guys can see my screen, yes?
Yes, you can see your screen.
Yeah.
Yes, sir.
Yeah. So
Yep.
I don't know what's happening on your side.
I will try to log in again to this meeting. I'll leave and come
Yeah,
back.
please maybe try to leave the meeting and then join again and try see if it works. Okay, so we were trying to figure out what's the derivative of 1 over sine. Okay. So for this, you can use the quotient rule. Okay. Remember, right? So let me just copy that there. Remember, remember the quotient rule for the derivatives. So what does the quotient rule tell you? When you have a function f of x divided by some other function g of x, and you're trying to find the derivative of it, and for our purpose here, I will always sort of write the derivative sign with the prime. Okay, so you guys will see that it's that's how you will use it. So the prime, that prime sign there. So in trying to find the derivative of that, the quotient rule tells you take the derivative first of f of x, you multiply that by g of x. So you first derive f of x, multiply it by g of x, right? And then you subtract f of x multiplied by the derivative of g of x. So this is for those who didn't memorize the identities, okay? Because the tricky things with the identities as well is that maybe you memorized it and it's fine, but if you forget what you memorized, how can you find those identities, right? So that so yes, and then you divide all of this by g of x squared. Right? So then that is the quotient rule for differentiation, right? So when you apply it to our problem here, which is 1 over sine, okay? Sorry, hey, sorry. When you apply it to our quotient here, you have, what's the derivative? F of x is 1, and our g of x is sine x. What's the derivative of 1?
0.
0, right? So you have 0 multiplied by sine of x, right? I'll just write it down so it makes sense, and then we'll cancel later. And then you have 1 multiplied by the derivative of sine x. What's the derivative of sine x?
Cos x.
Cos x.
Sorry, cos x, right? So cos x, right? All divided by sine squared, right? Because g of x is our sine squared. So all divided by sine. Please mute yourselves if you're not asking questions. Thank you. All divided by sine squared of x. Okay. And so now when you simplify this, please, can the person who has the microphone on, please mute themselves so there's no interference and people can hear. Right. So when you simplify this, 0 times sine just gives you 0. 1 times cos just gives you cos. So you have minus cos in the numerator. And when you divide that by the denominator, it's just sine squared in the denominator, right? Of course, you can rewrite this as minus cos of x, right? Divided by sine of x. Divided by sine of x multiplied by, right? So this is basically the same thing. Multiplied by 1 over sine of x. Right? These are basically the same thing. And cos over sine is cot. So you have the negative that comes back. Cot of x multiplied by 1 over sine, which we said was cosec. So multiplied by cosec x. And that's it. That's how you find the minus cots times cosec. Does everyone understand that?
Yes, we do understand. Thanks.
Right. Okay. Thank you. Moving on. Now let's try to substitute again. Maybe we can simplify this expression first before we substitute, right? We'll rewrite the minus cot x cosec into this form here, the minus cos over sine squared, just to simplify, okay? So let's try to do that. So I will copy this and then paste it there and then rewrite. So I'll do it step by step so you guys can follow along. So have minus cos of x divided by sine squared of x. It's in the denominator. And then this again can be simplified to be you're dividing one fraction by another, so you just multiply the first one by the flipped version of the other one, right? So in the numerator you'll have then sine squared of x, and in the denominator you will have in the denominator you will have minus x times cos of x, right? So that is what you have now. And when you substitute in the value of 0 here for x, you have sine squared of x, sine squared of 0, which is just 0, over minus x, so minus times cos of 0, which is 1, 0, 0 over 0 again. So you can apply L'Hopital's rule once more. Okay. So we can say applying L'Hopital's rule. I'll just call it H point R. Okay, so I don't have to rewrite the whole thing. H point R. We get what do we get? You can guys start. You guys should start already to derive the numerator. So try to derive sine squared and tell me what's the derivative of sine squared.
Is it not 2 sine x cos x?
Yes, it is. Thank you. So does everyone understand where that comes from? Sorry?
No.
Okay.
No.
So once again here, this is an identity. This is an identity that you guys should remember from your notes. So it's, let me just copy this so I can repeat it here. So remember the rule. When you have the derivative of some function f of x that is to the exponent of let's say n. N can be any any value, right? And as long as it's a number, it's an actual number, right? What you should know is that the derivative of that is the n you multiply, right, by the f of x, right? The f of x now to the exponent of the exponent of n minus 1, right? So you subtract this 1 from the exponent, and then you multiply that by the derivative of f of x. So this is another rule that you guys should remember. And this applies for any function f of x, trigonometric function, polynomial, any function that falls under, that is to some exponent, n, and n can be any number, right? So as you can see, if you substitute, for example, x to the 5 into this, our f of x is x, so you have now 5 comes back here, multiplied by x to the 5 minus 1, which is 4. So 5 times x to the 4 multiplied by the derivative of x, which is 1. So the derivative of x to the 5 is just 5x to the 4, right? So you can see that there's some identities that are sort of general enough that they apply to any sort of function, right? So now let's apply that to our expression sine squared, right? So now let's say we had the derivative of sine squared of x, and that we're trying to find here. Again, our n here is now equal to 2, right? So you have 2 multiplied by sine of x again, but sine of x to the exponents now of 2 minus 1, which is just 1, so I won't write that. So 2 sine x multiplied by the derivative of sine of x, which is cos of x, which gives us the answer that we got there. So does everyone understand now?
Yes, we do.
Okay, so moving on, what's the derivative of x cos x? I'm sure there's someone who already started doing that. So tell me, what's the derivative of x cos x? There you will use the product rule, which you guys should be aware of as well. And maybe in the meantime, I'll just rewrite the product rule. So it's here. I'll give you guys 3 minutes to find the derivative of x minus x cos x and tell me what you find, and then we move along. In the meantime, I'll write the product rule for those who don't remember it.
X sine x minus cos x.
Yes. Does everyone understand that?
Sir,
Yeah?
I'm a little bit confused. How did we change from in the numerator from the sine squared x to 2 sine x cos x?
I applied L'Hopital's rule. So L'Hopital's rule, you derive the sine squared x, you get 2 sine x cos x. That's what I just wrote here. Where?
It's an identity.
Down.
Is it an identity that the derivative of sine squared x is 2 sine x cos x?
Well, if you want to think of it as an identity, yes, but it's not really. Identities are more like general derivatives, like the derivative of sine is cos, the derivative of cos is minus sine, the derivative of ln of x is 1 over x. Those are sort of set identities, right? Sine squared of x is also can be thought of as an identity, but you can, I don't like to call it an identity, but just because you can sort of generalize it for anything. So let's say you had, for example, sine cubed of x, right? The problem is, the problem that I have with calling it an identity is that it makes it seem like you can only like memorize it and then you're good. But the problem is, let's say, for example, you have a question where they give you sine cubed, then whatever you memorize for sine squared doesn't count. So I think it's more important to remember the rule itself. If you remember the general rule, then you can apply it to any function. Sine squared of x, sine cubed of x, sine to the 4, sine to the 10, you can apply it to any sort of function. I don't know if it makes sense.
Okay, it makes sense. Thank you.
Yeah. Right. So going back to this is the product rule that I'm sure you guys should be aware of as well. And So if you apply this product rule here to the derivative of minus x cos x, you will find that it gives you, right? So for the sake of time, I will skip that step, but you guys, it's simple enough for you guys to apply it. So if you can apply it and then try and see what it gets you, right? So this is what you should get: x sine x minus cos x. Now, when we substitute in the value of x again, you have 2 sine of 0, which is 0, times cos of 0, which is 1. So in the numerator, you have 0, right? So basically, you have e to the, right? E to the, I won't rewrite the limit sign, I'll just rewrite the values that we're getting. E to the 0 divided by x times sine x, which is 0 times sine of 0, which is just 0, minus cos of 0, which is 1. So you have 0 minus 1 in the denominator. Right, so let me just rewrite the whole thing. 0 minus 1, which is just basically the same as e to the 0, which gives you 1. So does everyone understand this? Okay, so moving on to question 2, it's basically the same logic. You will apply again this exponential identity that you guys should recall from the notes. So you have that e to the ln of f of x is equal to f of x. And then when you apply it to this limit here, and maybe before we move on, you can substitute in the value of 0 and see what you get. As x tends to 0 from the positive side, you can clearly see that that is going to be equal to 0 to the exponent of 0 squared, which is just 0. So 0 to the 0. So you have to manipulate the expression once again to be able to solve it, right? So let's apply e to the ln of f of x to our problem. So when you substitute in the value of f of x there, we have that is equal to 10. That is equal to 10 of x to the exponent of x squared. Give me a minute. There you go. And then that should be just equal to 10 of x, right, to the exponent of x squared, right? So when you're finding the limits of that, you might as well just find the limits of the other one because they are the same. So now let's apply it to our expression and see what we get. So the limit as x tends to 0 of 10 to the exponent of x squared is the same as the limit as x tends to 0 plus from the 0 from the positive side of e to the 10x to the x squared, right? And once again, from the identities, remember that the x squared can come out of the ln sign, right? And what you have is in the numerator now, all you have left is not numerator, but I mean under the ln sign, you have ln of 10 of x, right? Which we can put in a bracket. And outside the sign, we have x squared. And if you substitute again the value of the limits here, oh, if you substitute the value of the limits, you get that you have 0 times the ln of 10x as x tends to 0, which tends to infinity. So you have 0 times infinity, right? So you can't use L'Hopital's rule for that. So you need to manipulate further. So let's manipulate and see. We can take the x squared here in the denominator, right? In the form of 1 over x squared, just like we did for the previous example, right? What's going on here? Yeah, right? And now if you substitute in the value of x, you will see that you have infinity over infinity, which is one of the cases where we can apply L'Hopital's rule, right? So you get basically e to the infinity over infinity once again, right? So that tells us that we can apply L'Hopital's rule, okay? And so let's do that. We can therefore apply h dot n, right? By applying L'Hopital's rule, right? What do we get? So you guys can already start to look for the derivative of ln of 10x and tell me what you find. Well, I'm rewriting this expression.
One over 10x times 6 squared x.
Just give me a minute. Sorry, you were saying?
It's 1 over 10x times 6 squared x.
1 over 10x times 6 squared x. Does everyone understand where that comes from?
No.
Right, so let's go through that as well. So we are trying to find the derivative of ln of 10 of x. Right. First, we need to know what's the derivative of a function ln of f of x. Okay, so let's generalize this. For a general function f of x, the derivative of ln of f of x is equal to, this is also an expression that you guys should be familiar with. It's equal to 1 divided by the function f of x, right? Multiplied by the derivative of f of x. Okay, so that's as simple as that. So now, why is this formula interesting? Because it's a general case for all sorts of ln functions, right? So it's different for logarithmic functions. So if you had log of if you had log of f of x, then it's something different, okay? But we'll go through that when we look at differentiation here. So, but when you look at the derivative of ln of f of x, this is the general formula that you have. And the reason why it's interesting is, let's say you have f of x is equal to x, right? So what happens when you have f of x is equal to x? You have that it's 1 over x, right? Multiplied by the derivative of x, which is 1. So it's 1 over x times 1, which is just 1 over x, right? So this is why I'm telling you that you guys should pay very clear attention to these general identities, because they will help you in so many cases. Now, let's try something even crazier. Let's say that you have f of x is equal to 1, right? Let's say you're trying to find the derivative of ln of 1, right? Clearly, you can see that ln of 1 is a constant, right? So the derivative of a constant should be 0. But just to show you that this formula here works for every case, right? Let's see how you get 0. So our function is 1. So now you have 1 over 1, right? Multiplied by the derivative of 1, which is 0. So you have that 1 over 1, which is 1. 1 times 0 is 0. So 0. You see? So when you know the general formula, then all the cases, all the possible cases for functions, you could apply them for that specific formula and it works out, always. So that's why I like general forms of formulas rather than memorizing a specific identity. Like you can memorize the simple stuff, like the basic stuff, like sine. The derivative of sine is cos. The derivative of cos is minus sine. The derivative. As soon as you know that, those two, for example, for trigonometric functions here in this case, you can basically identify all the other derivatives. Okay, so that's sort of a trick for you guys. Maybe you don't use it, maybe you use it, but at least you guys have it, so you know you can sort of use these tricks. Okay, so now let's apply it to our function tan of x now. Okay, so let's copy this and apply it to our function tan of x. So for our function tan of x, we have, what do we have? Well, we have ln of tan of x, which is just equal then to 1 over tan of x multiplied by the derivative of tan of x. And what's the derivative of tan of x? We remember that from our previous example, the derivative of, but did we even do a derivative of tan? Well, we didn't do a derivative of tan, but the derivative of tan is just cos x squared, right? And you can find that out by applying the quotient rule. Okay, so if you apply the quotient rule to
it's sec
yes.
squared, not cos x squared.
Oh, sorry, my bad. Sec squared. Yeah, sorry. I was thinking cosine. Hi. So sec squared, right? Yeah, sorry about that. It's sec squared. So when you apply it, you will see that you can find when you apply the quotient rule, you can use to the derivative of 10, you can see that you can find 6 squared. Right. So does everyone understand that?
Yes.
Okay, thank you. Right. So let's finish up this question quickly and then we take a break, okay? And then we move on to all the other problems. So we found the derivative of ln of 10, which is 6 squared over over 10, right? So let's just copy it into that. Right, and now what's the derivative of 1 over sine or 1 over x squared? That's you guys. What's the derivative of 1 over x squared? You can use the quotient rule here as well if you want. There's multiple ways to do this. Maybe you can use the quotient rule because we've seen it before. So try to apply the quotient rule that we used here and see what you get. Go ahead.
I think it's minus 2 over x cubed.
Minus 2 over x cubed. Yes. Does everyone understand how they can get that?
-2x to the negative third.
Yes, which is negative 2 over x cubed. Right. So I will let you guys apply the quotient rule there, and I'm sure you will be able to figure it out. Right. Okay. Then we can see if we can simplify this expression. So because right now it's a bit messy, so let's simplify it. And what we get in the numerator is x cubed multiplied by sec squared x, right, divided by minus 2 tan of x. Right. Okay. And yeah. So now let's apply, and that's as far as we can go. So let's apply L'Hopital's rule. No, sorry, not L'Hopital's rule, but let's substitute the value of x and then see what we get. So when you substitute x into this, you have 0 times sec yes, 0 times sec, which is sec squared of x is what? Is 0.
Hello.
Yeah.
Hi.
Oh.
Yes. Wouldn't you simplify it further?
Oh, you could, but I just want to like leave it like this because then we yeah, because then we can easily like because simplifying it further takes more time, but you can simplify it further if you want and then try to solve it from that. But you can also leave it like this, okay?
Okay, cool.
Yeah. So let's substitute in. You have x is equal to 0, so you have 0 multiplied by sec squared of 0, which is 1, right? So 0 in the numerator, divided by 2 times 10 of 0. 10 of 0 is 0 as well. So you have 0 over 0. So you can apply L'Hopital's rule once again. So now I want you guys to tell me what's the derivative of the numerator here, x cubed times sec squared of x. And here you can apply the product rule. So apply the product rule and then tell me what you get, which we just we showed here. So apply the product rule and tell me what you get. I'll give you guys 3 minutes and then we'll check it out.
Is it x squared times 2 secant tan x
Sorry,
plus
say that again. X squared times
2 secant tan x?
2 secant. Where's the 2 coming from?
No.
No. Okay.
Go ahead.
3x squared, 6 squared x plus x cubed, 2 6 squared x, 10x.
Plus x cubed. 2 sec squared x 10x.
Yeah.
Does everyone agree with that?
Yeah, she's correct.
Yes, we do agree.
Okay. Right. I'll give everyone else 1 more minute and then check if you get the same thing.
Can you say it again, please, Snetemba?
I'll say what you said if it's fine. It's 3x squared, 6 squared x plus x cubed, 2 6 squared x 10x.
Okay, yeah, got that.
You got the same thing.
Yeah.
All right. So I will go under the assumption that your guys' calculations are oh, okay. Just give me a minute. All right. Okay. So 3x squared sec squared x plus 2x cubed sec squared x multiplied by 10x. Right. What about the denominator? What's the derivative of 2 10 of x? This one should be
Negative 2 sec square x, I think.
yes. So negative 2 sec squared x. So now here as well, we might have to simplify the expression to sort of make our job easy, right? So we can see that sec squared is a common factor in the numerator and the denominator, right? Can you guys see that?
Yes.
Yes, sir.
Right. So since you can see that, it means that you can simplify it everywhere. So let's simplify it and see what we get. So simplifying the sec squared in the numerator, we remove it there. We remove it there. And then what we get is that, okay? And I think that's as far as we get simplified. So now let's try to substitute in the values now of x. If we put 0 in the numerator, you can clearly see that you'll have 0 in the numerator. 0 divided by -2, which is just 0. So you have e to the 0 once again, which is equal to 1. Does everyone understand that?
Yes.
Okay, so we are done with these limits. we'll move on to differentiations and stuff like that. And then, so I'll take, let's take a 5 minutes break. So let's start at right about around 1:15.
You don't need
Okay.
the break, sir.
Sorry?
You don't need the break, sir.
You might not need it, but I do.